Okay, good morning, everyone. Welcome to the distinguished lecture series in energy at the Texas A&M Energy Institute. We have the great pleasure of welcoming here with us Dr. Ilya Zaslavsky, who's joining us from San Diego University of California, San Diego. A little bit about Dr. Ilya. He's the director of the Spatial Information Systems Lab at the San Diego Supercomputer Center at the University of California, San Diego. His research focuses on distributed information management systems, particularly spatial and temporal data integration, GIS, and spatial survey data analysis. Dr. Ilya earned his PhD from the University of Washington in 1995, specializing in statistical analysis and reasoning models for geographic data. He also holds a PhD equivalent from the Russian Academy of Science Institute of Geography for his work on urban simulation modeling and metropolitan evolution. Dr. Ilya has led several international research collaboration efforts in several fields, including serving as co-chair of the OGC WMO Hydrology Domain Working Group, an international group of experts developing standards on water data exchange adopted around the world, as well as co-chair of the Global Water Information Interest Group of the Research Data Alliance. Dr. Zaslavsky has been also invited as a prominent national and international speaker to different venues, including the Library of Congress, Rio +20, and Kyoto Forum, and has received funding from several organizations, including NSF, NIH, the USDS, so Department of State, and Microsoft, SV, and other organizations. Dr. Ilya, it's a pleasure to have you with us today, and we're looking forward to learning more from you on leveraging AI and large language models to navigate the water, energy, food, health nexus. Please, a round of applause to Dr. Ilya.
Thank you very much, Basil. Round of applause is a little premature. let me talk. I'm very happy to be here. Thank you for inviting me. My first thought, what am I going to tell energy researchers? I'm not an energy expert at all. I was trained as a geographer and worked on urban simulation modeling. I also worked with what was sort of a Russian branch of the International Systems Research Institute in Austria for some time, then moved to this country and got another PhD in totally different field. So for the last 25 or so years, I've been pretending to be a computer scientist, but basically trying to combine what I remember from geography with what new computer science ideas and technologies bring to the fore. And recently I learned that what I've been doing for so long is now called Nexus. So I'm going to use this word repeatedly in this presentation. Nexus, of course, is about connecting different things, about data integration, and organizing multiple sources into some kind of system that helps you solve problems is what I've been doing in all of my projects. More than that, I learned that, well, it turned out that two of my grants actually had Nexus in the title. One of them is the project that we have with a wonderful group from TAMU, and that is so-called Global Center on Climate Change, Water, Food, Energy, and Health, Nexus, of course. That is something I'm going to talk about. Another project is somewhat more modest in terms of the broad extent of topics that it covers. It just focuses on water and energy, and it's part of NSF Proto-OKN initiative that goes much deeper at the technical level, trying to work with a lot of water data sets and energy data sets, giving you the ability to query all of them. Now, I'm going to run fairly quickly through my misunderstanding of what Nexus is. Please feel free to ask me questions. It will be much more fun for me and for you if we have a dialogue rather than me talking for a long time. We'll get started. So Nexus, of course, is about how things are connected, how the system works, how when you have multiple components in the system, how you distribute resources in a way that different parts of the system develop in unison and in some kind of harmonious way, and how you describe the system such that each part of it has a set of measures of indicators that are sensitive to interventions. It's somewhat manageable, possible to do it when you just have two sectors. I can show you, later on that it can go pretty deeply into kind of technical approaches of how you do that and how you bring this data together. When we are looking at the three-sector Nexus, that's probably the most popular these days. If you looked at water, energy, food Nexus, there are lots of papers on this topic. Again, later in the talk, I will show you analysis of literature that shows that there are not that many papers that talk about the four-component Nexus: water, food, energy, and health. Only about 200 or so that are specifically focused on the versus like thousands and thousands that deal with three-component Nexus. And you're all researchers in this area, so I don't want to spend time on various examples of how Nexus works. So we need to look at water efficient irrigation, and this is how water and food production are connected. There are certainly connections between water and hydroelectric power and energy production. Food and health are strongly related, as you can imagine, because what you eat is what you are, right? And all of that is influenced by changes in climate and changes in environmental aspects of our lives. So different diagrams, and there are tons of them if you just search on Google, and this is more or less random examples that show how components of water, energy, and food are related. And then we try to add the fourth dimension. And it becomes really, really challenging because health can be described and presented in so many ways. And information about which components of health are critical for certain vulnerable population or individuals. This is not something that is given to us as hard science. There are lots of studies that may show fairly controversial results. So typically you are trying to present this as sort of an approach where you have, you can play with different allocation strategies. So you can allocate resources into each of the sectors, given that they are somehow related to each other. And this can be presented as actual indicators or some kind of scores, like in this paper that I showed. However, when you're trying to integrate medical studies in this, it is a challenge. It is a challenge. So you may have seen this graph, because this graph has been around for 10 years or so. The story was that people took a cookbook and looked at like 50 ingredients and tried the most common ingredients. For each of them, they tried to find whether these ingredients would be causing or reducing cancer risks. And you see it's all over the place. So how do you deal with this data? You can't really average this data, right? Because that will be average temperature in the hospital. Some people have high fever. That is, you can't, you probably see that there is insufficient semantic granularity in these charts. So there is red wine and white wine, and they may affect cancer risks in different ways. So Same things with other components. If you look at milk, right? Well, the entire Nexus is subject to dramatic realignment in the next few years, right? Because RFK Jr. comes with strong ideas about milk, as you may have noticed. He's a big proponent of raw milk, which means it shouldn't be pasteurized. It's mad cow disease or avian flu or salmonella are welcome to contribute to your health. So how it will happen, it's hard to see. But what I'm trying to say is that this is the situation. And when we're trying to bring health data into water food energy nexus, we have to sort out through which of these factors are really important and indicative of public health and can be used to forecast health dynamics. At the same time, there was another, I think that was a related paper saying, why should you always never believe single medical studies, with some interesting statistics. Out of 101 new therapies, only 5 made it to the markets. You should basically believe what is written in medical journals unless there have been confirmation and reproducibility studies that would be able to. You can say that this was 10 years ago and things changed. I wouldn't say things changed that much on the medical field, but we have a lot more machinery now to be able to bring these type of claims into a system where the claim may provide some confirmation to, where the system may provide some confirmation to these claims or detract these claims, or you can have sufficient evidence that allow you to trust this or not. And I'm talking about the big changes that happened in how you write papers, assess papers written by your students, in how you actually do your everyday work. This happens with large language models. All of you have used large language models, I assume, right? You know that's it's a double sword when it gets to energy, because they are very energy consuming models, but at the same time, they change the pattern in which we do work in such a dramatic and useful fashion that they're probably here to stay. And the companies who offer such large language models, they pay enormous amount of money for energy. It's kind of interesting to see how they will survive at this level, but apparently it's worth it because the market is there, and the number of people who get on this bandwagon and using large language models increases dramatically. So we can ask LLM. Let's say we have a bunch of controversial claims. Ask what LLM thinks about that. Of course, beware what you ask any authority like that, because I'll get to that later and show you examples that you need to be very careful about how you ask queries and how you prepare the LLM to answer those queries. But also, we may want to narrow research to some specific topics and perhaps not look at all components of health, but focus on one disease and how that disease is affected by climate change and how it affects other components of the nexus. That's one of the projects that we're working on. So in here, I try to look at some of the projects that I've been working on and try to see how they would answer the questions that we see in the previous slides. Narrow it down, make conclusions over large volumes of information that bring together all the best data that is available for a specific domain. That's what we're trying to do in another project called water energy Nexus open knowledge network. We want to understand when we're asking LLMs, do they really know what kind of picture of the world they have? If we throw in some questions onto the model that it hasn't been trained on, do we still expect a reasonable answer? And for some questions, we certainly know that that's not the case yet. We have another project where we looked at allocation of strategies to combat, allocation of strategies to measures against pandemics, against disease outbreaks. There is a simulation model that shows what will happen if you invest in strategies, but that simulation model is a very large one and for the entire county. But counties are very different internally, right? If you look at San Diego, there's east part of the county and there's the coastal area. There's downtown and there are military bases. It's very different. People work differently in different parts. So we cannot really apply the same allocations everywhere, but do we want to take an 800 parameter model and make 100 of them so they don't show how they interact with each other? It's just impossible. So we ask LLM to do that and see if it can help. It can help in some cases. And it's important to understand where it can help and where. So I'll talk a little bit about that. Another way to apply AI and large language models is to, and this is also related to food. That's a project funded by NSF called Nourish. It's funded under the Convergence Accelerator program, where we are trying to build a set of tools to encourage entrepreneurs to bring healthy food to market. And they have all sorts of questions. Which areas would be the most appropriate for different types of food? What regulations they have to face? Where to get the funding? Where to get the next phase of funding, and so on. So we have conversational interfaces that help them do that. And finally, I will get to my favorite toy project called SUAVE. SUAVE stands for Survey Analysis via Visual Exploration, and show how we can actually analyze the entire academic network behind these things. By the way, how much time do I have? Can I go until like 3 o'clock?
10 minutes before, so we can allow some.
Oh, okay. Yeah, and since I started talking about my project, this is my lab. We work on all sorts of things spatial. So mostly spatial data integration, which is, I guess I would now tell my students that this is Nexus. Interoperability and standards. So I've been co-chair of a group at OGC that developed watermark-up language. GIS, geospatial databases, COVID modeling. So we were among the first who did brain mapping in a way that would be set up against a set of coordinate systems that we defined for the brain, so that multiple people around the world who would do brain mapping could ask a question, where else in that part of the brain, or where else have you seen that particular signal? Okay, and that required that brain slices had to be placed in a certain coordinate system that would be defined against feature landmarks in the brain. That's my toy projects that I will show you, and a few others. And I also teach spatial data science. It appeared as part of a book because it happened to be one of the first courses offered in the US on this topic. The course focused on data science kids who are experts in coding, and they just need to get some flavor of GIS spatial data libraries with a lot of Python coding that's used in visual machine. So now I will tell my students they need to know to learn yet another concept, Nexus, and well, they have enough new stuff. Okay, so the project that we work on with Dr. Rabia here and his group, and with folks at UCSD, and actually quite a few collaborators around the country, is called Global Center on Climate Change and Water, Energy, Food, Health Nexus. And my small part there is to develop data foundation. So basically to support advanced modeling that is done here, and to make the data findable, accessible. You may have heard of that abbreviation, FAIR, making data findable, accessible, deliverable, reusable. So basically, if you're coming, if you're not part of the project, want to understand the data and find the data, it will provide you sufficient information for you to be able to use. I will jump to an application example, because in this project we are trying to show how, first of all, we catalog all available data. And unfortunately, there is not much available data for Jordan that would reflect those 4 components of the Nexus. And we have to, yeah, and by the way, so that's a way to sort this. You can sort this by type of variables. So you can sort this by, let's say, select all data sets that deal with population. So that's sort of a quick way to sort things. It's another example of SUAVE application, but much more convincing examples. And for any of these topics, or for any of these data sets, you can actually get more information about them and launch applications, including LLM and machine learning applications from here. So, for example, here's some information about this app, and I can launch an application connected to it, and that would allow me to develop maps. So that's fairly straightforward kind of approach, but it will also let me query a large language model and see what it knows about, let's say, sanitation. This is information that is available from WHO database about sanitation. So all of these variables, we can grab any of them and see that it will retrieve the data for Jordan for different years. And now we can start asking anything we want about the data. Well, I shouldn't say anything, because we actually have to train the system to understand some of our questions. But I can ask things such as, we have some questions on the side, charts, value. See, I can type things that are not necessarily, well, that can have mistakes, right? Misspellings. It will still understand the core meaning and will be able to produce the graph. Or let's say which year has the highest. Well, that was even worse. But it didn't understand what I was asking. So basically it said the country with the highest percentage of population using safety map is Jordan, simply because it's subset of the Jordan. But if I would be a little bit more careful typing in, it would probably give me something more correct. So yeah, highest value was. So what can we do here? We can take natural language queries, convert them into specific instructions for the LLM. And how it happens, I capture that text. I add a little bit more of a context to LLM. So look at, tell it, look at Jordan, look at, highest value, or can be, basically look at the largest number that you have in this array. Look up the year when that happened. So when I give it to the LLM, it can answer this question. So I have a bunch of templates that allow LLM to answer such questions. That we took that approach a lot further in another example that I'm going to show you. That is with Wenokian project. And by the way, you are very welcome to follow along. This is kind of a simple URL to remember. You will get to this data set, this collection of data set. For any of them, there will be an explanation and there will be some application example. I'm not showing you all of them because that's okay. I think these were just my backup slides in case things don't work as a demo. So I'll quickly run through them. Yeah, search WHO. And currently we don't have that many queries that we can answer, but adding them basically means if you feel that there is a query, something like that, add a few additional sentences for the LLM to understand what's going on and to be able to answer. The problem with these data set, with working with Jordan, of course, data is very valuable. It's very difficult to get people to share their data. We fortunately have good connections with Ministry of Health, and I got these 3 files without actually zero metadata for these files. But I know that one was called LCD, that is probably non-communicable disease. That's mother and children health and infectious diseases. And we can look at the top diagnosis. You already see that there is some inconsistency in how these diagnoses have been assigned. Some of them are like essential, hypertension not essential, or something like that, or not specific. Some capital letters, some non-capital. In infectious diseases, it's actually even worse because you have like scabies in capital and scabies in lowercase, and they, according to a computer, they're different diagnoses. Then when you actually start trying to map this data, you see that some diagnoses happen to be popular between 2019 and 2023 or till 2022. So for example, benign hypertension stopped being diagnosed after that. And the first time they diagnosed essential hypertension was in 2022. So trying to make sense out of that is actually not that, and I'm just trying to show you that dealing with health data, even when we have a large database, it's not that trivial, because when you are looking at these examples and we're trying to map, to chart the most common diagnosis here, you look at that and you feel that you need to congratulate Jordan Ministry of Health because they eradicated diarrhea. There's no more diarrhea after 2023. We assume that that's not the case, and that's the case of medical coding. But how to do that medical coding correctly and will affect how we actually process the data. And that requires that we take an additional step of trying to make this data fair, well described, well documented, findable by well-defined codes, and only after that we can plug them into model. The next step is we want to, and by the way, we now have another application, which is something I'm not going to show today, which will take any data set and will try to give you an assessment of whether this data set is fair and ready for machine learning applications. And if it's not, then it will do some manipulations. It works on single data sets when we have a situation where we need to relate, let's say, climate data or weather data and health data. So this is climate data by stations. This is also climate data by stations from another source. That's most of these data sets we have in the system. And we can try to kind of map them over our health data. The problems are health data happen to be aggregated at the level of governorates in Jordan. So this is like states in Jordan. And the climate data happen to be by points. These are weather stations. How you relate them to each other, it's unclear. We have to make some assumptions. Let's say if the weather station is within the governorate, then we will link them. But whether that is a correct link, you cannot really say without doing much more detailed studies of this relationship. And without a lot more data. So this project is trying to narrow the scope to just energy and water in this case, and try to ask exactly these types of questions about how things are related. This is NSF initiative focused on Proto-OKN. OKN stands for Open Knowledge Network. And basically it's a collection of knowledge graphs which organize knowledge as graphs, where you have objects that are connected with other objects with links, and these links have labels and objects have labels. So you'll understand what graphs are. So imagine that facts are organized in this fashion, and you can do reasoning over such collections. So this system is composed of a bunch of projects. If you click here, you will see that there are three groups of projects: those that deal with specific domains, like in our case, it's water and energy, those that bring all the data together, and those that do the education part. Some of these projects would be especially useful to connect with if you are trying to engage health data and interested in specific pathways that need to be looked at when you are trying to see how, let's say, environmental change results in specific health outcome. One of them, yeah, the SPOKE project is one that is run out of UCSF and Stanford, and they have strong connections with Google. They have built a very large graph that deals with biomedical events. That's something that we discussed yesterday. But our project is this one, and I'm going to show you how we use large language models to query across multiple data sets. Yeah, so there are actually a lot of partners here. UEFH, for instance, for urban flooding. That's another knowledge graph that's called Internet of Water that is supported by USGS. Nowhere graph that has been supported by NSF. previously, and all of them have built large collections of facts organized as graphs that can be queried via Sparkle and GeoSparkle. The problems are very familiar. These data are managed in isolation. We need to build really a Nexus framework to bring them together. That's why it's called Water Energy Nexus. So that we can answer questions, is there sufficient water supply for energy or for other needs? What is the demand? What are the threats? And how to answer that? Let me show you the application that actually is somewhat more developed than what I showed you in the previous project. And I will try to give you examples. There are about 30 examples of how you can ask queries. These queries are merely templates, so you can modify them and it will still work. So if you have any favorite queries, so for example, find all counties that Sewater River flows through. That implies that you have to get a river from one knowledge graph, you have to get counties from another knowledge graph, you have to get an understanding of what it flows through means, because that is a spatial operation that may not be supported. And underneath, a query plan is built that chops this natural language query into several GeoSparkle portions and then collects the result. So you end up with a set of counts. Let's look at some queries that deal with energy. For example, find all dams located upstream of the power station, such and such, along the given region. So in that case, it will go to a database of dams. It will go to hydrography information where the upstream notion of upstream exists. And it will go to all power stations, which is yet another data set. And yeah, the hydrography. And so bring this all together by querying multiple data sets and combining information in staging. So it constructs a query which should not be part of a user-friendly interface, but for now we're still developing things. No, yeah. So it gave allocations of those dams along the route. So the queries here are merely templates. You can change the specific operations. You can change the specific data sets that you're asking for, because on the background, there is a very large collection of data organized as not a single knowledge graph, but as multiple knowledge graph maintained by different. The infrastructure, I should say, is very fragile, because if one of these knowledge graphs is offline, then it will say, sorry, cannot answer your question. And that actually happened a lot. That usually happens about one day before there's an important demo. We gave a demo of that at NSF 2 weeks ago. And like 2 days before that, they decided to update nowhere graph, which means certificates are wrong and the schema changed. Okay, that was a fun weekend. Anyway, getting back to the presentation. So there are lots of data sets, and there are actually a lot more. These are just data sets, edit more recently. Actually, one thing that I wanted to show you, you can also ask about regulations. How they determine if my facility is subject to NPDES regulations. And this is a large book of regulations that we have encoded, and you can ask questions about it. So it will actually give you text saying that, well, what you should look at when you are you're in this situation. You mentioned this. This type of approach is now being used across multiple projects when we have conversational interface in the Nourish project, where we ask for, where the user may ask for what kind of regulations I have to keep in mind when I want to start a food business. We'll give you that based on local ordinances and California Department of Public Health rules and stuff. Now, of course, LLMs are wonderful, but we want to make sure we understand the limits. And unfortunately, the limits are very easy to figure out at this. Even with good models like OpenAI and Claude model, they are really fantastic. They know a lot, but still, when you're trying to ask things like, where shall I locate healthcare facilities? It will not necessarily know that healthcare facilities may be located already nearby. Okay, so in this situation, we have a large Stella model, right? Many of you are familiar with Stella. And I don't know, there are some gory details about how we try to make use of that model. You can have a nice interface over it. Basically, it's all done in the context of a serious game. So people who are public health managers come to play this game with us. They are given scenarios. Let's say you see an outbreak with, let's say, 20 people, 20 cases recorded of monkeypox. And then the next 3 days, you have 50 people with monkeypox. And these are such and such demographics and such and such. What do? You have a list of about 20 strategies that you can choose. Where do you put your money? So then users, then judges will take those responses and plug them into a model and see which of them actually produces better results in terms of SEIR. You're familiar with epidemiological models, so we want to minimize number of infected, the I in that SEIR. So we're trying to see what if we replace people with large language model. Will large language model be able to allocate resources in a way that would actually make more sense because they know everything, right? And we build a system where we wrap the Stella model into some Python code. Well, the story is actually a little bit more complex because Stella is not really an open system. You can't really wrap them. It has, you can export XML file out of it and then try to build, to import that file into Python. That is going to fail because, okay, perhaps I'm going too far into our terrible experience of trying to work with Stella. So eventually it was already written in R and started to work. And the idea is that we have a model that runs for the entire San Diego County. It has about 800 parameters. Now we want to make sure that we can run it for any specific area in the county because the county is very diverse. As I said, we have areas along the coast, we have areas in the east, they have totally different population, totally different problems and capacities. So our allocation should be different. But we don't want to create for each of these areas, for each of the zip codes, a model that has 800 parameters because that will take forever, and we don't have the data. So we just ask large language model to do its best to figure out what should be the allocation strategy. I should say that ChatGPT and GPT-4 generally is better than open source models like Llama. It at least would know that if you're talking about zip code 92093, it's university. And this means that it would make sense to invest into strategies that are university related in that zip code. Other models don't know it. So the results were fairly patchy, I would say, when you are trying to invest to give you a vector of investment by strategies in a given zip code. And one of the strategies is to increase capacity. It normally would not take into account capacities in the neighboring zip code. So the picture of the world is very uneven. It knows something such as where universities are and that universities can do more work with respect to strategies that deal with university, like vaccine research, student focus matters, but it wouldn't know much about these things. This is the area where we are trying to kind of do some research work and figure out what actually is on the background of large language models that it produces. So beware what you are asking, but try not to ask questions that involve spatial dependence so far, unless you have interest. So that is very quick. Since we're talking about food, another project that I should mention is Nourish. And these are pretty staggering numbers, right? We spent the entire revenue of food industry in the US is 1.8 trillion, but we spend a lot more on diseases that originate from food production by about 150 billion per year, which is a big number. And the problem is, of course, with ultra-processed food, with hyper-palatable food. So these types of foods are the focus of our of this project. And another focus is trying to come up with a set of AI interfaces that will help users figure out what are their regulatory constraints, what is the optimal location for them to locate their business when they try to bring tomatoes or vegetables from from a nearby farm. Given market demands, given specific conditions in the area, given a lot of other characteristics of the area, such as foot traffic, such as proximity to highways. So anything that we can glean from local geographic data or from Esri geo-enrichment. And business center, because there are multiple people that multiple financial organizations try to support this activity, but they work only with certain types of customers. So you have a fund that will release money in chunks of $20 million. That's not going to help a small entrepreneur. So how to make this entire system work is part of the project. And finally, I know that I almost have no time, but I wanted to leave you something to play with. I looked at, so that's the same SUAVE system. That's my toy project that I mentioned earlier on. Whenever I see anything new and like fun coming up in the AI world, I just put it in here and try to come up with applications. And sometimes these applications actually stick. So here, I was trying to look at everybody in the world who have ever published papers with words water, food, energy, health, Nexus in the abstract or in the title. And also, when you look at three component, you have, but let's look at just this one. So you can see how they are distributed by, say, countries. You can look at, say, folks in the US. You can zoom in and see the names. Let's actually look at Tamil, because we know that this is the place where we can look at this Nexus. So affiliation is Texas. And here we go. We have Basel here. And yeah, let's try this. And Dr. Rabia, we can click on any name. And again, this is not something I've worked on for too long, maybe for 20 minutes, because the process of how you develop that is you enter a collection of keywords that you search on and a bunch of words that you want to tag these results with. And then it just spits out this thing, which has all concepts that have been attached to each author. I have a list of collaborators. These are collaborators. I have all publications on this topic, so I can click on show me publications, and you may have recognized some of them. These, they all have abstracts. So basically, on any topic that you are trying to explore, you can construct this type of bibliography for yourself. And you can also see how these folks are connected with other people. So there are two clusters of researchers from Tamil. Here we have Dr. Tabai Mokhtar, and Basel is also here, and they work with a bunch of folks from other countries. But then there is another cluster with Qing Zhang, you know anybody under this name? So anyway, so this is how you work with this system. And if you want to look at the entire network, you see that this research at the moment is very clustered. So lots of people work on this topic, but there are not that many connections between them. And you can also see how in more developed fields that there will be more connections. You can also see how that changed over time. So in 2004, there was not much, but then you can see how the network started to get bigger, and how additional clusters started to appear, and how some of them started to connect with each other. Anyway, this type of information system, as I said, this is my toy thing, that it's free and open source, and anybody are welcome to it. And I guess I'm still within my time to show the last slide. So LLMs can play, and AI in general, can play a very useful role, because you can use that to facilitate integration and try to find which specific indicators are sensitive, how you conceptualize the place. They will give you a summary of which variables would be useful to work with. Improves prediction, dynamic models. So we try to connect LLM with system dynamics models, and with an experience that did not show that it's a winner yet, but at least what the problems are. LLMs and knowledge graphs. This is a very kind of a topic that many people are working on these days and trying to use them together, and that's what WEMK is about. Obviously, you can ask LLM, explain me Nexus for a 5th grader, and it will actually, I haven't tried it, but I was told that it's possible. So it's a very good tool for knowledge dissemination and collaboration. And there are obviously lots of challenges, some technical challenges that I tried to work through, some energy footprint challenges, because there are several things that happen when you work with this model. The models need to be trained. That's a very energy intensive operation. And then you can imagine that millions of people then start hitting this model. And so reasoning now has the increasingly takes increasing share of costs. So much more than just training. Well, anyway, I'm not an expert in this. So I'm not an expert in energy. And we're about to hit 12.
So thank you very much.